Mutual inductance of two long solenoids. So here we consider two long solenoid having a common length L, and these two solenoid, they are S1 and S2. So this S1 I have shown it with a black color, and the second solenoid S2, it is drawn with a blue color. So this solenoid S2 here, it is wound over the first solenoid S1. Okay, so these two solenoid, they are wound in such a way that they are so close to each other, that means in a very compact manner, and hence the two solenoids, right, will have the same area of cross section. That means the area of cross sections of this solenoid is A. Similarly for the blue one, because it is wound very compact, then the area of the second solenoid also will be A. Same area. And similarly the radius of the two solenoid, right, will be R. Okay. So now, to find out the mutual inductance of the two solenoid, we will do in this way. So because two solenoids are here, then different currents will be passing through the two solenoid. A current I1, let's say, it is passing through the first solenoid S1, and a current I2 is passing through the second solenoid S2. Okay, now let us imagine that this current I2, it is passing through the solenoid S2, whereas at that time, we imagined there is no current I1. Okay, so because of this current I2, which is passing through this blue solenoid, then what will happen? Right, this current I2 here, right, we can say it is a varying current. Okay, it is a time varying current. So because the current is varying in this case, so a magnetic flux, right, will change inside the solenoid S2. Okay, okay. Now, this current I2, which is passing through the second solenoid, will also produce what? A magnetic field inside the blue solenoid. So this magnetic field, let's say it is B2. And you know very well about the expressions of the magnetic field inside the solenoid. It is equals to mu naught n I. Okay, but n here, this small n, it stands for which solenoid? For solenoid number 2, so I'll write subscript 2. Similarly, the current which is passing in solenoid here, it is I2. Okay, what is N2? Where N2 here is equals to the number of turns per unit length. So because we are considering about the second solenoid, so this number of turns mean N2, right? And length, what is the length? Length is same. Okay. So N2 is the total number of turns in the second solenoid. Okay. So this is the magnetic field inside the second solenoid. Now this magnetic field inside the second solenoid is a changing magnetic field. And so the magnetic flux which is linking with this second solenoid will change. Alright. Now, because the two solenoids, right, as I said, they are winding in such a way that they are lying so close to each other. Hence, the magnetic flux which is changing with respect to this, the magnetic flux which is changing inside the second solenoid, that magnetic flux will also link with the first solenoid. So in that case, the magnetic flux in the first solenoid becomes how much? We know magnetic flux is equals to BA. But in the first solenoid, if we have N1 number of turns, then the total magnetic flux inside the first solenoid will be N1 BA. And now what is B? B is the magnetic field which is produced by the first solenoid, and this A, it is the common area. Alright? Okay. Or I can say phi 1 is equals to N1. Instead of B, I'll write mu naught N2. Okay. Sorry, I made a mistake. Actually, when I say phi 1, it means the magnetic field which is linking with the first solenoid. So for that, write this B, it is not B2, but it is B1, which is the magnetic field inside. We imagine in that way. But it's the same thing because B1 and B2, right? The magnetic field which is present inside the first solenoid is the same as the magnetic field inside the second solenoid. So I will write either B1 or B2. Okay. So that means B1 is the same as B2. So instead of B1, I'll write mu naught N2 I2 times A. So this is the magnetic flux. Or this phi 1 is equals to N1 mu naught. Now how much is N2? N2 is the number of turns per unit length in the second solenoid, and for that we write capital N2 upon L times I2 times A. Okay? Alright. So this is the magnetic flux inside the first solenoid. Okay. So if this is the magnetic flux, then this magnetic flux, right, it is linking with the with both solenoid, which means if this is the magnetic flux inside the first solenoid, then how much is the mutual inductance in this first solenoid? So the mutual inductance of the first solenoid with respect to the second solenoid, it can be written as M12. When I say M12, it means mutual inductance of the first solenoid with respect to the second solenoid. And this is equals to how much? If you remember from the expressions of phi is equals to Mi, then the mutual inductance in this case, M would be how much? Phi upon I. Or I can say, but in this case, phi is phi 1, and the current, it is due to which current? It is due to the current I2, right? So far, we have not considered any current in the in the first solenoid. So the current which is producing this magnetic flux, it is due to the current I2. Okay. Now M12, it will be how much? Instead of phi 1, right? You substitute this value, which is mu naught N1, N2, mu naught N1, N2, A, I2 upon L. And with this I2, you can write it here. Now this I2 with this cancel, so this mutual inductance of the first solenoid with respect to the second solenoid becomes like this. Okay? Alright. So this is my equation number 2. So in a similar way, if you imagine that a current I1 is passing through the first solenoid, but the current I2 in the second solenoid, let's say it is 0. So when you allow a current I1 to pass through the first solenoid, then this current I1 will set up a magnetic field inside the solenoid. So that magnetic field, it is how much? B1, and this is equals to mu naught N1 I1. Alright, where N1 is equals to how much? N1 in this case would be capital N1 upon L times I1, where this N1 here stands for the number of turns in the first solenoid. Okay, so this is the magnetic field inside. So this magnetic field here, right, it is a changing magnetic field which produce a changing magnetic flux. And that magnetic flux, it is linking with both the solenoid. So I can say the magnetic flux which is passing through the second solenoid, it would be how much? Same like this, NBA. But the number of turns, right, we are considering for the second solenoid, so number of turns is B2. Number of turns is N2, and the magnetic field is B2. Okay. Or phi 2 is equals to N2. Instead of B2, right, is the same as B1, so you can write mu naught N1 I1 upon L times A. Okay. So if this is the magnetic flux which is linking with the second solenoid, then how much is the mutual inductance? So the mutual inductance of the second solenoid with respect to the first solenoid is equals to how much? It should be phi 2 upon I1. Okay? Sorry. This is, it is phi 2 upon I1. Now, this M21, again, if you substitute this phi 2, it would be this value. So because of I in the numerator, so with this I in the denominator will cancel, so you'll get finally mu naught N1 N2 A upon L. So this is the mutual inductance with the second coil with respect to the first coil. So this is my equation number 3. So looking at these two equations 2 and 3, we see that the mutual inductance in the two cases is the same. So therefore, I will remove the subscript 1 and 2. I will just write M, which is the mutual induction in the two solenoid, is equals to mu naught N1 N2 A by N. So this is the expressions of the mutual inductance of a two long solenoid. Okay, so again, if you look at this equation, we found that this mutual inductance depends upon the number of turns of the two solenoids. Also, it depends on the area of, the common area of cross sections of the solenoid, and upon the length of the solenoid. Okay, so this is about the mutual inductance of two long solenoids. Okay, if instead of air core, let's say inside I insert an iron core having a relative permeability mu r. So if you insert an iron core inside the two solenoid, then the mutual inductance becomes mu naught mu r N1 N2 A by N. This is the expressions of mutual inductance of two long solenoid with an iron core inside it.